Okay, hello everyone. Thank you very much for joining. I'm going to talk about the practical approach to error handling. First of all, a few words about me. I'm from ThinkCell. I'm the current development lead here at ThinkCell. And we are doing an add-on for PowerPoint, which doesn't sound terribly exciting, but we are kind of like the super PowerPoint add-in on steroids. So we do things like hacking around PowerPoint, disassembling PowerPoint, putting in hooks and rendering UI on top of it and all kinds of things. That's not what I want to talk about today. What I do want to talk about is our approach to errors, really. And 20 years ago when we started, we had to kind of think about, okay, how are we going to deal with errors? Because errors occur everywhere. And we need some sort of unified approach of how we would deal with this topic. And what I'm going to talk about is precisely that. Now, first of all, a little intro. Of course, we know that errors can happen anywhere, and we all want very reliable programs. But of course, we have no time at all to write error handling code. And the question is, what do we do? How do we deal with this problem? And as I said, that was the question that we asked ourselves when we started ThinkCell. And basically, I want to present you with the result of how we actually did it. For the good past 20 years now, we've kind of refined that strategy a little bit here and there, but fundamentally, that's what we stuck to. Now, first of all, I want to talk about a little bit about where errors are coming from. That's not terribly exciting, but for completeness, I just want to go over it. So you say you have a file and you're opening it, say here with a constructor, and that file doesn't exist, right? So what happens then? Well, first of all, how could you transport this information out that the file doesn't exist? One way would be with some return value, right? So you just return whether the file opened or not. Of course, that doesn't work for constructors. So for constructors, what you could do is an out parameter. Not terribly pretty, but it is a possibility. Both clutter the code with checks. So you have to check everywhere whether an error occurred. And of course, you can forget that check. And the newer C++ standards, they now have a way to warn you if you forgot by annotating at least the ones with the return value with no discard. So you have to somehow access the return value. You can't just discard it. For the out parameter, we have no such facility. One other way to transport errors out is our error flags. And for better or worse, so that's the default for C++ IO streams. They do have that ability. The way it works is that on the first time an error occurs, a flag is being set. And later on in the control flow, you can query that flag and check whether all the previous calls succeeded. That's great if it's possible, because you only have a single control path through your program. You first do all your calls, and at the end, you can find out whether everything worked. You don't have to kind of bail out at every single stage. This is fine, and this is very practical if checking at the very end is good enough. So if you're, for example, writing into a file and any one of these writes failed, it's probably enough to know that at the very end, when you're finished writing the file. Now, when you're reading a file, well, you need intermediate results, and there you have to probably find some other solution. As I said, it's used for C++ IO streams. It's also used, for example, when you issue calls to a graphics card. So there you're often batching all the calls together and pushing it to the graphics card. And once the whole frame is done, you can ask, well, did that frame succeed? Is all the writing, did all the writing go well? And if it didn't, then you kind of reset the graphics card or something like that. So there it's also quite common, this approach. There is another technique that also tries to get into that tries to further this goal of having a single control path for the success and the error cases, which are monads. It's essentially like a STID variant on steroids. So you're kind of packaging together the result as one option and some sort of error information as the other option. And that package is then moved through the program using various utilities. And so doing that gives you the single control path, which is easier to reason about than if you are, have these many control paths for all your error conditions. The C++ standard is probably going to give us something that helps implementing these nomads. There's the paper P0323 right now at revision 11, so they've revised it many times, and it's going to introduce state expected, which is a monad that you can then use to transport error information or the result. Now, of course, the prime way to output exceptions or output errors are exceptions. That's probably the go-to place when it comes to error handling. There are a few things to say about exceptions before we go into the pros and cons. So you should always catch exceptions by reference. If you catch them by value, you risk slicing. That means that of this whole derived object, only a part gets copied into your value, and you kind of slice off the rest of the object, which is usually not what you want. And what's bad about that, in addition, is that when you copy something and it requires allocating memory, then if that allocation fails, you have a double throw, and that will terminate the program. It will cause to terminate. So it's probably better, really, to catch exceptions by reference. One thing that I didn't know when preparing this talk is that if you're writing a symbol throw semicolon, this will actually throw the original exception. So even if you if you caught by value and you sliced, the throw semicolon will actually throw the original. So that's I found that kind of curious. It's not terribly relevant. Usually, if you catch by reference, then you kind of expect that. But yeah. So that's how C++ is done. Now, there are code bases that don't allow exceptions, and there are probably good reasons. They work a little bit like a multi-level go-to, because they introduce every time an exception is thrown, you have an extra control path that goes from that location where the exception is thrown to outside of your function. It's kind of like you intersperse these code paths throughout your code base, and and these code paths per se are not really visible. You don't really know which functions are throwing exceptions. So, for example, here there's a main function calling an increment, and that increment happens to throw. Suddenly, out of that n equals inc of n, there is and I annotated it here. There's an exception coming out of it, which is kind of bailing out of that current control flow and going to the catch clause. And in our code, we annotate these places where exceptions are being thrown, so you at least have a chance to see which kind of control flow, what kind of control flow is in the program is happening. So if I could rephrase this, if I'd be mean with go-tos. So you could say, well, there's an increment, and if the throw condition is true, then I'm just going to go to the end of the program and there kind of return out of the function and transport the type of exception out via some sort of side channel, like an out parameter here, and to be processed outside of the call. And then in main, where I receive the whole thing, there is this special, if I got back from the increment with an exception, then I'm just going to do a go-to into the catch block. So you get these. This is just to illustrate that you get all these control flows, and yeah. So and you can write actually on Discord if you have any questions. And I'm glancing at my Discord here once in a while. So I keep track of your questions if you have any. Now, of course, you could say, well, you should, Arno, you with your exceptions and your dislike for exceptions, you should stop whining. Because, of course, we have to write exception-safe code, right? And every good code is exception-safe. So this really shouldn't be a problem. Okay, so what do we mean by exception-safe code? And exception-safe really is not really specific to exceptions. It's kind of is specific to failures in general. What kind of things should we do when failures occur in our function? Now, the easiest case is the never fails, right? So if a function that never fails, then you don't have to handle anything. You don't have to do anything special. And that's certainly, that's very good for you as the implementer. And that's very nice for the caller because she doesn't have to deal with any of the problems because your function failed. Now, that's often impossible, of course, because, well, we may do things that may be able to fail. And in that case, the next best thing you can do is to provide a strong exception guarantee. That means the function may fail, but it will actually restore the program state to what it was before you made the call. So the call essentially is transactional. Either all the effect of the call takes place or none of it will take place. Now, this is possible to do and also very desirable if you have library functions. In application code, on the other hand, it's very hard because usually applications do many state changes in a sequence, and you would basically have to find a way to batch up all these state changes and then roll them back if any one of these state changes fails. And this would possibly consume a lot of memory, require a lot of code, and just be a very complex endeavor in general. Now, there's something a little bit weaker than that, which is the basic exception guarantee. And so in that case, the function may fail, and it will restore the program state in that case, but only to some valid state. So whatever is left over will be valid, not necessarily what it was before. You may think, well, that doesn't sound too bad, but I mean, can you imagine there's this customer call, that support call to Microsoft saying, hello, is this Microsoft support? I was writing a book and suddenly it all disappeared. And Microsoft says, oh, that's all okay because we only provide the basic exception guarantee. And then the customer's happy to get this explanation, say, thank you very much, and have a good day. Now, this is very unlikely to happen, right? So I'm questioning whether this basic exception guarantee buys you a whole lot in practice. Okay, now we are kind of back to square one, right? So here's the challenge. Error handling is a lot of effort. In development, we have to be super paranoid because everything that we do could fail and we have to deal with it. And we have to write all this error handling code, which creates a lot of extra code. And then in testing, you have all these code paths that you have to test. Because as we know, if you don't test them, they won't work. And overall, you have a whole lot of work on your hands for the development and for the testing. And at the same time, you have very little customer gain because the customer pays you to solve problems, not to handle errors. So the question is, what do we do? Okay, so here is what we do at ThinkCell. First of all, whenever we do a call, that's something that could fail, we check everything. We check every API call, and we have wrappers for every kind of API call we make from Windows. There are some functions that report errors with setting a get last error threat variable. There are some functions which return an H result. On Unix, you have Arno, also threat variable. So you're kind of wrapping all these calls to check whether all these calls succeeded, and if they didn't, how they failed, what kind of error they actually returned. We assert very aggressively. So we have many asserts in the program, and the asserts stay in the release version of ThinkCell. So we ship them to the customer. Now, if a function is not expected to throw exceptions, we mark them as no except. So when an exception is thrown inside such a function, terminate is being called. But if you have something throwing exceptions unexpectedly, you're pretty likely to crash anyway, to terminate your program anyway. So that's not so bad. But that gives you a good opportunity to install a handler with std set terminate that to allow for some checking, to allow to collect information about that exception that was unexpected. Now, after we did all that, and after we instrumented all the code with all these checks and all these wrappers and to collect basically whether any of these things fail, we assume that everything works. So we don't write any error handling code for now. We just assume that everything is okay. Now, of course, the question is, what do we do if something fails? So why do we not write any handlers? Well, we don't write any handlers because we want to keep the set of code paths small, and more importantly, to keep the set of program states small. So you want to narrow down the set of states in your program to the set of states that are essentially where everything is working. And then maybe if you have some failures somewhere, that would require you to handle these failures, to introduce additional states, additional things which you usually don't have to deal with, but suddenly your program becomes more complex. And it's not only in the code paths, and I think that's more important, that's in the states, in your variable states that you have in the program. You also want to keep that as narrow as possible. And so what do you do if your checks fail, right? So if the checks fail, priority number one is we want to learn about the error. We want to learn about what failed. So we try to collect as much information as possible. If that happens during testing in-house, that's great. You can just go and look at the problem. It may happen only on the customer machine. Then we are trying to gather as much information as possible in a memory dump, and send that memory dump home. Send the memory dump to us and at ThinkCell for analysis. Now, if it happens on the server, it's much better actually. You can actually stop the thread and notify the developer or the operator and let them hook up with the debugger onto the server and see what went wrong. Now, gathering information is priority number one. Only priority number two is to carry on somehow. Now, if you just failed a critical check, and the things that I discussed are essentially critical, you didn't program for them, you didn't write handlers. If such a critical check fails, the program behavior is now undefined. We don't really know how the program is going to react if something fails that we didn't program for. So even if the program will continue running somehow, we will not send any further reports, because any reports we send may just be a consequence of the first thing that actually failed. So we are from now on, we are silent. One important thing, if an assertion fails that we are shipping in the program, we don't terminate. We keep going. Because experience shows that assertions can be wrong. And so they may actually fail, although everything is fine, the program will actually carry on just fine. And if you would then terminate the program, you would essentially penalize the developer who wrote this overly aggressive assert. So as a consequence, developer would be very cautious to write any aggressive assertions. They would write only the things that I really feel safe about. And that way, you wouldn't document the program as well as you would if you write aggressive assertions. You want aggressive assertions. And people have to be able to get things wrong without getting any penalty. So that's why I strongly advocate carry on after assertions failed. Now, if you need some safety, if you say, oh my God, if the assertion fails, that may indicate that my data got corrupt or that my nuclear power plant melts down. You need to add that at a higher level. So, for example, what we do for the server is you stop processing certain categories of requests if the handler for that request repeatedly stopped working. And that may mean it either went into an infinite loop or it stopped working because it's waiting for the developer. Remember when an assertion fails, we'll stop the thread. So many threads will go into that state, and then all these threads get eaten up. And that may mean that many threads got eaten up by that. Or it may also just be a regular infinite loop, right? Maybe someone programmed an infinite loop, and that would have the same result. The thread just disappears and is never coming back. And if you have too many of these, you could say, well, I'm going to stop processing these kind of requests. Something similar you can do in a desktop program by, for example, regularly saving the state. If you're having an autosave every minute, that would mitigate the consequences of any crash that you may have. So once you did that, the thing is, how do we proceed? What do we do now with our failed API calls or failed assertions? What we need to do is, first of all, we need to reproduce the error at home. So we need to sit down and take the information that we gathered and see whether we can reproduce the error, whether we really understand the error. Because you only want to add handling code for errors that you reproduced and that you actually understand. Otherwise, the errors that you are handling, your error handlers, they are either never used or they are never tested, and they do the wrong thing. And experience shows that 5% of the handlers handle 95% of the errors. So you have these very few errors which are reasonably frequent and that you really need to handle. And there, it really matters to get good quality for your software. It matters how well you handle them. So, for example, we had one case where the XML parser, we used a component out of Windows, which was an XML parser, MS-XML, and when we instantiated that MS-XML, we had quite a few cases where we couldn't instantiate it. It would throw an error. And the natural consequence or the natural remedy would be, well, we put up an error box and saying, well, sorry, your XML parser is broken. I can't do anything about it. But it turned out that pretty much all cases of the MS-XML not being able to instantiate was because it wasn't properly registered in the registry, in the Windows registry. So what we did is we added code to re-register MS-XML in the registry and then try again. And suddenly that function that regularly failed on the customer machine became super reliable and the problem just went away. And that was very good. We didn't need any error box. We didn't bother even the user. The user wouldn't even know that something failed. We just fixed it in the code. And that's really what you want. That's the kind of error handling you want. Something that doesn't bother the user. You want to work around the problem somehow. I want to go briefly through the categories of errors that we have. So, and over time, we kind of developed these different kinds of categories. And since it took time to do that, I want to share them with you. Now, the first thing, of course, are critical errors. Examples are like a null pointer access, for example, or an API call that is not expected to fail, that's suddenly failing, or it's even failing, it's expected to fail, but not with this particular error code. So we wrote a handler that handles a particular error code, but that it may not be the right handler for this particular error that's thrown now. Or, of course, you have failed assertions. Also, that would fall under this category. Now, they're treated as if they basically never happen. You don't write any handlers for them. And it's a little bit like C++ undefined behavior. The program state is invalid afterwards. We don't report anything more. And carry on and hope for the best. So that's client, send the report, and then we disable future reports. With the server, I already told you, we're going to notify the operator and go into an infinite loop because priority number 1 is gather information, right? Priority number 2 was carry on somehow. Here we can actually gather information in the best way by just preserving that thread, because you can directly attach with the debugger and look into all variables. That's much better than a memory dump, say, where you may not have certain information available anymore. Here you can really do everything. You can even skip over the error in your code. You can get the instruction pointer over the error, and maybe you can just carry on, keep running that thread. Now, should we notify the user about critical errors? The way we do it is we only notify the user if a false alarm is very unlikely. And as I said, assertions may be wrong. So if in case of a failed assertion, we actually don't notify the user. We just carry on silently because, again, you don't want to penalize your developers for writing wrong assertions. Otherwise, they will stop writing them altogether. Now, here's another category of errors. It's untested. So the way they come about is, let's say you have a hook function where you have for a API call register foo. So there's a register foo that you didn't write, it's just happening, and you hooked it because you want to keep track of all the foos. And the register foo returns whether it was successful. And if it was successful, then you have to keep track of that foo that was registered. But if it failed, then you assume that the foo just wasn't registered, and then you don't have anything to do. So far, so good. But the thing is, maybe during testing, you never had a reproduction for register foo failing. It was always successful. And so you always kept track of foos. And the question is, if that ever fails, what kind of effect does it have on the rest of the program? Does the caller of the program, which may not be you, or the caller of the register foo, which may not be, as I said, we program add-ins, so maybe in this case PowerPoint, they call register foo and register foo fails. Well, it may very well be that PowerPoint goes belly up afterwards. So this is maybe something that you would like to know. How does PowerPoint deal with this problem that you actually never that you never had and that you was never able to test in the lab? And did we test it proactively? I mean, we could have mocked register foo and just inject an error. Well, I mean, if it never fails, right? Then again, this is wasted effort. Then you don't need to do it. But still, if it does fail, you would like to know. And then you still have, the opportunity to investigate, and maybe then during the step when you reproduce the error at home, you could just mock register foo to fail, and then see how PowerPoint behaves, for example, if you can't get to this information on the customer machine. But in general, it's something you just want to be informed about if it happens. It doesn't mean that the program behavior afterwards is undefined. You think you wrote the right thing, you wrote the right handling code, and you just said, okay, I'm only going to do something if this thing is successful. But you still want to know if it fails because you've never seen it. What we do in this case is we send a report. So we inform our developers, and we also throttle any future reports. So this may happen. Maybe PowerPoint has tons of register foos to register. So it's calling register foo many times, and if they all fail, then you would just have the whole PowerPoint application busy sending error requests, error reports to you, and you don't want to do that. So instead, you just say, okay, if you send already 5 reports, then we're just going to throttle. We're just going to tune down the number of reports and not going to send anything anymore, or only send something every minute or whatever. Now on the server, you can send the report. It's probably fine, and then you probably don't want to halt the thread because it's not really proven that the program behavior is undefined. You think you've done the right thing. Would it be possible to assume that register foo always succeeds? Yes, this would have been a distinct possibility. If you're reasonably sure that register foo always succeeds, and if you think, well, accommodating a non-working register foo is going to be kind of complicated, then one option would be to say, oh, register foo, I'm just going to assume it always succeeds because I haven't proven, not been proven otherwise. Okay. Now, here's another category, bad user experience. Say you have a third-party bug. Sometimes PowerPoint makes shapes disappear. Now, it's reproducible. You have it in the lab. It's supported in terms of your program behavior is still defined, and it has been tested. But if it happens, it's very likely that the user is going to be unhappy. So what do you do in this case? Well, you probably don't want to send a report because, you are getting informed about something that you already know exists and you've already seen it in the lab and tested it in the lab. But you may want to log it because if you don't have any other error handling, if you don't have any other user-friendly way of telling the user, which again would take time to write, and if it's rare, maybe it's not worth it, you just log it. You just say, well, this is the situation that happened. So if someone calls, then the support engineer can look at the log and say, she had the experience of this PowerPoint bug, and suddenly the shapes disappeared. And now you can explain the behavior, or you can decide, well, this is the third time I got this call today. Maybe it's time to write some sort of handling code, or maybe call up Microsoft so that they fix PowerPoint. All right. There's another category of errors, which is the indication of that something is broken in the environment, that this is a special situation on the machine that you're currently running that may lead to problems. We have a situation like this, for example, with add-ins, when they hook the same function that we hooked, so we log that. Or, for example, things like the operating system reports something weird, like we have a space as a decimal separator. something that's not typical, like not a period, not a comma, but something weird. And we would support both. We are happy with having spaces as decimal separators, but it would still indicate that something is odd on the system, something special. So in this case, because this specialty of the system may cause a problem. And what we do in this case is that if the client calls and our support engineer would actually hook up a support session, then we actually set a flag and then we would notify of this particular situation. So the support engineer would get a pop-up, not the original user when she originally ran the program, but only the support engineer attached to the program. She would actually see, okay, there's something strange at least, and that may, since the user called because something didn't work, this may very well be the reason for the call. This may be the consequence of this particular special environment that the computer's in. Okay, so once we send all these things to the server, these reports, what do we do with them? They are usually sent automatically. And if the user opted out, we also have a way for the user to send a prepared email. So she can actually click on some button and say, I want to report this error to ThinkCell. Once the report reaches our servers, these memory dumps automatically are opened in a debugger, and they're analyzed, and we see in which file and line the error occurred. We of course have access to our debug symbols. And then we make the memory dump and the error details accessible to the developers. So they have a little database application that shows all the errors, and you can filter them. You can prioritize them by various ways. And developers can also mark errors as fixed. And you just input the version when you fix that error, and that will actually trigger automatic updates. So if there's an update available that goes to a version where the error is fixed, that update is automatically offered to whoever has this problem. And if this problem has been reported by email, then you can actually send an automatic email back and say, well, that's my recommendation to update to this particular version, which when we introduced that, we got some calls where they said that this is kind of magic. I mean, how are you able to work that fast? Well, that's the magic of computers. All right. In our environment, in our application, it's quite frequent that problems are related to the customer environment. Otherwise, we have in-house testing, and that in-house testing would have found the problem. Now, these memory dumps that we send, they have a list of loaded modules. So that's DLLs in Windows or the dulips for macOS. Now, can you identify the module that is causing the error, or even the versions of the modules that are causing the error? How could we go about that? So we have a database with all these reports. Say we have 12 reports, and we know all the ones which are actually from that particular problem, where the particular problem occurs. And we also have many of them where this particular problem did not occur. A different problem occurred, but you can kind of use these as our background distribution. And so we have some that are special, they have that problem, and others don't have that problem. Here it's 6 occurrences out of 12 reports have that problem. Now, along with that information, whether that problem occurs, we also have module information. So here we have, say, 2 modules, and module A occurs in some reports and module B in other reports. In this case, module A actually occurs in 3 out of 6 occurrences that did have the problem, and 3 out of 6 that did not have the problem. So it's about even. So you would think module A doesn't have anything to do with the problem. Now, module B is kind of skewed towards reports that have this problem. So 4 out of 6 have this problem, 2 out of 6 where they don't have this problem. That don't have this problem. And the question is module B, is that strong enough to say, well, module B may have something to do with the problem? can you kind of quantify how likely is it that module B is at fault? Okay, so how do we do this? The idea is we use some statistics, in this case, minimum description length. The idea is we are kind of compressing the description of the world. And our little world in this case is the information whether a particular report actually has the problem or doesn't have the problem. Now, and the question is, if I know that there is a module B, for example, in that report, does it help me predict whether that report is actually having the problem? And if that helps me predict whether this report has the problem, that means probably module B has something to do with it. It helps predicting. And this prediction can be used to improve compression. If I'm a really good predictor of my data, then I compress it better. I can compress it better. Now, what we use for compression is arithmetic compression, the Laplacian estimator. It essentially estimates a probability P that a report has a particular problem. And initially, it's using an uninformed prior, so all the probabilities are equally likely. And if you use that to compress, then the number of bits to compress, the number of bits that you need to compress n bits with k ones or k zeros, same number, is logarithm n plus 1 times n over k. And just to illustrate what that means, the number of bits becomes smaller if p is closer to 0 or 1. So if you have 12 bits with 6 ones, you need 13.55 bits. If you have 12 bits with no ones at all, it only takes 3.7 bits to transmit. Now, why is 13.55 bits more than the 12 bits you originally needed to transmit the information? Well, that's always the case. When you're doing compression, you always, for some data, you need less space, but there's always, because of the pigeonhole principle, for some other data, you will need more. So there's no compression algorithm that compresses everything down. That's impossible. All right, so how does it work now for our reports that we want to compress? Now, first of all, we have that baseline. We have 6 out of 12 reports having the problem, which is 13.55 bits. Now, if we just make use of module A, we don't expect any improvement, and we just want to check whether that's really the case. So first of all, we have to say, well, we have A and B, both 2 modules. We have to pick A over B. That already takes 1 bit. That's something we have to transmit. We are going to use that module as a predictor, essentially. And then we do 2 different estimates. We take all the reports that have A and compress them separately. Why do we compress them separately? Well, because we are assuming that all the reports with A have different probability characteristics than those without A. I mean, that's the whole premise, that we are saying A has something to do with the problem. A is a good predictor whether the problem occurs or not. So we're compressing all the reports with A, and that's 7.13 bits, and all those without A, that's another 7.13 bits. So total, you get a 15.26 bits. So module A has nothing to do with the problem because 15.26 is more than 13.55. Okay, now we do the same thing with module B. And there, you again need 1 bit, but now you have 4 out of 6 or 2 out of 6, so you need fewer bits to encode your occurrences of the problem. That's 6.71 bits each. Now the total is 14.43 bits, and that's still not good enough to be relevant. So versus the 13.55 bits. Okay. Still not good enough. So 4 out of 6 not enough. What do we do? Well, let's see, we have a module C, right? And that occurs 5 out of 6 times if the problem, among the reports where the problem occurs, and only 1 out of 6 times when it doesn't occur. So now we choose this module C over module A and B. And now we have 3 modules to choose from. So it's the binary logarithm of 3, which is 1.58 bits. And now we compress all the reports with C and without C, 5.39 bits, 5.39 bits, and total is 12.37. So it's relevant. So our system would say module A, module B, they are not relevant for the problem. Module C is relevant. And in practice, you get basically this compression gain for many modules. And if you're having many modules to choose from, you have many more hypotheses. So it's becoming even more important to consider what it costs to basically say, okay, I'm going to prefer this one module over all the other ones. It works in the same way if a module fixes a problem, because then it will actually predict that the problem doesn't occur. So that is just without you doing anything, it'll fix that problem. It'll do that as well. We also extend it to module versions. So we have various ranges of module versions. So we try like up to a certain version number, or from a version number up, or between two versions. We have all these hypotheses in there. And again, it takes more bits to transmit which hypothesis we choose. And that way we can get a pretty good prediction of kind of if or in which kind of modules or module ranges have to do with the problem. Okay. There's one thing I want to talk about at the end of the talk briefly, which are the C++20 contracts. They are a new language feature that was supposed to be introduced to C++20. It's kind of like an assert on steroids. You can declare function pre and post conditions declaratively. So here's like precondition is expects, and then there's the replacement for asserts, which is ensures, or actually ensures post condition. So expects precondition, ensures post condition, and then there's assertion, which is just serving as a regular assertion. Just slightly different syntax, and it's more standing out as having documentation character. Now the problem is when they wanted to introduce this feature, there are many questions, and these are kind of the questions that we talked about in the talk here. So how do you check the contract? When do you check the contract? Do you check it in debug? Do you check it in release? Are there actually contract conditions that you never check, that you just want to have as a documentation? Now, what do you do if the contract gets violated, if the check fails? Do you terminate? Do you carry on? Do you report something? Well, what do you report? To whom do you report? All these things are many variables, and people had different ideas about what to do under under different scenarios, and it was very hard to get agreement on all these things, which is why it got removed from the C++20 at the last moment, and this discussion of what to do is now going to continue for the next C++ version. All right, thank you for watching, and yes, we are recruiting. That's why we're doing all this. hr@thinkstyle.com if you're interested. Yeah, so I'll be over on Discord, and if you have anything, then you can find me there. All right, thank you very much.